Okay. Ok.
Partiamo.
Quando dovremmo essere a posto? Senti?
Buono.
Siamo. Bene. Quando vuoi partire,
Okay.
partiamo.
Forse bisogna chiudere il microfono dal tuo lato, Stefano.
Dal mio o dell'altro PC, adesso lo faccio.
Sì, perché c'è un po' di... Buono.
Bene. Quando vuoi partire, partiamo.
Ok, forse bisogna chiudere il microfono dal tuo lato, Stefano.
Dal mio o dell'altro PC, adesso lo faccio.
Sì, perché
Quando vuoi partire, Nicola, con l'introduzione?
Buono. Con this computer. Okay. So, good afternoon to everybody. It is a pleasure this afternoon. We have an invited lecture in our Foundations of Databases course. The lecture is given by Moviri. Moviri is a leading company in advanced areas of engineering. So Moviri focuses on consulting for large businesses with a specific focus on performance engineering, security, analytics, and IoT. Moviri is actually a multinational company and also the center of a cloud of startups and very innovative companies. So it's really a pleasure to have them here today to talk with us about performance engineering from an industry perspective. And it is also good to know that Moviri has now opened a hub here in Padova, so it is a great opportunity for working also with them for internships and whatever. Today, we have two people from the Moviri team, Giovanni Gibilisco, who is head of engineering, and Stefano Cereda, who is a senior data scientist and also PhD candidate at Polytechnic of Milan. So this is also to really show you that after the master, you can do a PhD, and it is still a very good choice if you are interested in industry and in cutting-edge technologies. So this is to say that a PhD is not just for working in academia, but really to stay on the top of the technology. So guys, it's really a pleasure to have you here today, and please start.
Okay. Thank you, Nicola, for the introduction. So, as Nicola said, I'm Giovanni Gibilisco, head of engineering in a company which is called Akamas. And you see Moviri also in the slides. It will be clear to why you have these two names here. And Stefano, which is a data scientist also in Akamas. This presentation about a little bit about our company, just the very beginning, but the core of the presentation is about the discipline, actually, which is called performance engineering, which is something that sometimes is taught in universities. There are some classes of performance engineering, but it's also a discipline that is very useful in enterprise environments, in production environments, and this is something that we do for our customers. So we want to give some hints on how what you might study in a performance engineering class is used in an actual environment, in a production environment. In some big enterprise environments. So you might imagine banks like, I don't know, Intesa, Unicredit, or telco companies like Vodafone, Telecom. So these kind of environments are very huge and complex. So we want to share with you our experience in working in those environments. So what is managing those environments from a performance point of view, and how we do it nowadays with the current discipline, and how we embed some research activities that we do in order to make this manual effort, which is quite hard to do, smarter and smarter. And this is what we do actually in Akamas. So I will start with a few words about our company. Okay. So as the professor said, Movieri is a company that was actually founded by some professors from Polytecnico di Milano. It was actually one of the very first startups of Polytecnico di Milano. Now it's a much bigger company, more than 200 people with offices all around the world. And Movieri is a consulting company, but it also has some software companies. So we do software development for our software, we sell to our customers, and we do consultants. We are very expert in a few fields. We are not a generalist consulting company. We don't do software development for our customers. We don't do many other things that much bigger consulting company do. We try to be very, very expert in a few fields and recognized by many hard customers, I would say, on these fields. The first one, from the historical point of view and from the numbers of people and revenue, is the performance engineering, which is what we are looking at today. We are also working in other fields that we will not cover today, which are analytics, security, and IoT, Internet of Things. And for each of these, we do consultancy, and we have a software or product company, mostly, that tries to bring innovation in these fields. For performance engineering, the software company is Akamas, and this is something that we will see in this presentation. For analytics, the software company is called ContentWise. You might not have heard of it, but you have used it. If you have ever used any Italian provider or even some American or UK streaming providers, you might get a recommendation. You might watch this movie. That recommendation is mostly by ContentWise. So it's started off as a recommendation engine for your movies, your TV series, and these kind of things. And it evolved to a much bigger version, which also might recommend you clothes, newspaper to read, or these kind of things. So this is an application of some algorithms that comes from data scientists to a specific domain, which is a movie and then UX personalization in general. Security, we have also another software company here, Cleafy, which you might not have heard of, but you mostly use it because it protects a few hundred million people using their credit cards, bank accounts from online frauds. It analyzes the traffic, the usual behavior of users while using your card or while doing a bank transfer. And if you see something strange, they might ask for another layer of security. They might ask you to send an OTP or another password, understand the risk of your transaction. And from Internet of Things, we have a strong partnership and part of the company of Arduino, which is one of the biggest maker platforms. So this is the reality Movieri. As I said, the Movieri was founded in the year 2000 by some professors in Polytecnico di Milano with a strong focus on performance engineering. We mostly invented the first software to do capacity planning, which is one of the activities of the field of performance engineering. Capacity planning is mostly focused on understanding if your data center capacity is fine and how to evolve it. Imagine you're a bank. You own a data center, which is an entire building full of servers that is serving your customer, and you acquire another bank a little smaller than you. You might be UniCredit acquiring Monteri Paschi, another bank. You forecast that in your next month you have a user base that will increase by 20%. Is your building enough? Are your servers enough? Do you have enough room for them? You have to merge the data center. Can you do something more efficient? Can you reduce the load on some of these servers or these kind of things? Capacity planning is mostly trying to answer this kind of question, looking at historical data, how your application were running in the last year, in the last months, and try to predict what is going to be in the future, making some assumptions on the business or on the applications. we created a software which was called Kaplan, standing for capacity planning, not very innovative as a name. That was then acquired in the year 2010 by BMC, which is a huge US company. And we kept going on by producing more companies. I already introduced you all of those and what they do. And so, doing so consultancy in those areas. So when we find that there is a business opportunity and some research that we are doing that fulfills that need market, we try to spin off a company and launch a new product. So that's more or less what's going on. Akamas is the latest board. We invented basically a couple of years ago, trying to bring in some optimization approaches that we will see later. We'll see how the algorithm works in the field of performance engineering. So Movieri is quite big now. We have offices all around the world. The two main are the headquarters in Milan, near Polytechnico, near the university. The other main office, I would say, is Boston. So, because we have a global footprint in terms of customers and also in terms of offices there. But we also opened a hub here in Padova, in Via Sant'Andrea. We've just been there for the time. They are still building up some rooms. This is the very first room that you see there in a quite nice building. So we also have a local presence here for some of our customers that are in this area and for some of our colleagues that live here and usually work in this office or come to Milan sometimes to work in the other office. And we are trying to also build local hubs in Italy. This is the first one that we opened last month. Okay, so what is performance engineering? Performance engineering is quite broad. The main idea is to care about not functional requirements of the application. When the software, you have functional requirements. Your software has to do this, has to do this. If it doesn't work, your user cannot do what they want to do on your software. If Gmail doesn't work, you cannot send email. That's the main purpose of the software. If Gmail works, but it loads in 2 minutes, it sends an email and it's received 5 minutes later, it's working, but you're not very happy with it. And if you think about retail software, if you think about the Media World website, for example, if you're trying to buy a laptop and you go on the Media World website, if it doesn't load in 10, 15, 20 seconds, you're probably going to Euronics or Amazon or any other provider that can sell you the same good. So non-functional, these are called non-functional requirements. Non-functional requirements like response time. This is one of the metrics, for example. So the time it takes to respond to a request, to load the web page, for example. Or CPU consumption. How much does it cost Media World to engage to some of these companies to run their infrastructure? You might run the same infrastructure on your laptop, it's very well optimized, or on a rack if it's not optimized. So the cost of the two is really different. This is another side of the non-functional requirements. And you have different activities that you do, all related to this performance aspect. The first one is designing. So you can design software to be performance efficient. So look at the software, how it's designed, how it's used, the data, and how it is used, the resources that you have. The part is observability. So in these companies, usually there are some rooms that are where people for 24 hours a day look at the performance metrics and see how the software is doing. So if you are a bank and you are doing wire transfer or credit cards or managing credit cards, you always have someone looking at the system to check if the system is fine. And the performance engineering is trying to understand what to look at this huge and complex system, building alarms to detect if there are issues. I have a fun story about this. In Netflix, I was in a conference where they told the story a couple of years ago. Netflix had what they seem to be a huge outage in all South America. So there were people looking at this dashboard, looking at the network traffic of Netflix red box, which are the boxes that are deployed in the different cities with the movies that you stream. And they suddenly saw a drop in the traffic from the whole South America region. So they say, okay, there is a huge outage here, and there are alarms going by, and then people trying to understand what's going on and trying to fix it. At the very end, they found out that Brazil was playing soccer at that specific hour, so no one was watching Netflix, but everyone was watching the soccer game. But that is an example of what happens when there is something strange. So what metrics do you see? They were monitoring network traffic. This is some of the metrics which are quite deep metrics, but they give you a nice picture of your environment and what to look at when there is some problems. So this is part, which is we help customers build this monitoring system, managing them, and helping them when something breaks down to identify the actual issue of the problem and solve it. Then another part is about preventing these issues in the first place. We are in the Black Friday week. Usually, I would say 100 people, for example, 100 people per hour try to buy something on the MediaWorld website. Since this week is Black Friday week, they are experiencing some load which is 10, 20 times higher than their usual load. But they design the application to work 99% of their time with a certain load in mind. They are now experiencing a peak of load which is way higher than they usually do. So having an application that is robust enough to scale out or scale up to support this workload is quite hard. Black Friday comes once a week and you know exactly when it comes. So you can prepare for it. Preparing for it means running tests. Running tests means designing how you are using an application and try to simulate this before it happens. So this is another part of performance engineering. And we will see a bit more about this. Some of the activities that we do in the performance engineering field. As I said, as a consulting company, we try to be very expert in this particular field. Akamas is the software company related to performance engineering that we created a couple of years ago. Basically, it tries to do this complex activity of optimizing an application for performance metrics in a completely automated way. We've seen a bit how this is done. The why is that because doing this kind of activities requires a lot of experience. If you want to optimize a Java application, you need to know how Java manages memory. You need to know that there is the heap. The heap is divided in different regions. The garbage collector that works to free the heap in the different region. That when a certain type of garbage collector is running, the application cannot serve workload, and this is seen by some spikes in the response time. This is something that really happens, that I did this analysis quite a lot of times, but it requires me to have a strong knowledge about Java. If you're talking about .NET, might be different. If you're talking about Python, might be different again. Python has the global interpreter locker, which works in a different way for parallelism. There are a lot of stacks, a lot of languages, a lot of software there, and they all work in different ways. I cannot be expert on all of them, and being very expert, some people build their own career in being expert in one of these. They might be Oracle masters, and database administrators that know everything about Oracle, but I know nothing about SQL Server, for example, or some other software that is not a database, but a web server like Nginx. So having this huge amount of expertise is hard. So we are trying to build something that learns from the different experiments, trying out different configurations and different tests, and understand what's the best for your specific application. So this is what Akamas is aiming to do. We are going to see now we already jumped off a bit in the performance world. Now we are going deeper in what is performance engineering and how we do it. We will see first the performance testing. So try to doing a performance test, what it means to do a performance test, all the different steps. And now what it is to doing it in a continuous way, so in a repetitive way. And then we switch from testing to optimization. So, okay, we've done our test. Now what? If the test was fine, okay. If the test was not fine, then we have to do something to optimize the application. And then we take a look at some of the techniques that we use under the cover in Akamas, which are based on some machine learning algorithms quite advanced in this field, and then we compare them with state-of-the-art, which is basically some optimizer done by Twitter and Facebook and these other companies that are doing this in their production environments. So first of all, a few words about two key performance metrics. There are a lot of them, but I would like to introduce two main metrics that you will see in more or less every system. The first one is throughput, which is the amount of work that you do, the amount of requests that you do in a certain period of time. If you go to McDonald's, the number of hamburgers McDonald's serves every minute, for example. If you look at the web server, it's the amount of requests that your web server is serving to the customers. The other response time, so is how fast your hamburger is done. McDonald's I don't know if you saw the movie on McDonald's, they built the entire system to reduce the response time, to reduce as much as possible the time from you asking your hamburger to getting your hamburger. So they optimize for that specific non-functional property. So there is the time spent to cook that hamburger. And they also have a nice throughput. This can be transferred to a load that is from the performance tier, the little low. And so some things also come up, not only in the IT fields. But these are two key differences. And if you want to optimize your system, your IT system, so now we talk about IT system. For this property, you might build two different systems. If you want to transfer a huge amount of data from Europe to US, get a ship full of hard disks and move the ship to the US. The ship has a huge payload in terms of terabytes and petabytes of data that it can move. It takes 2 weeks to go from one point to the other. So 2 weeks later, you have all your terabytes, whatever you want, on the other side of the ocean. But if you're, it's fine if you want to move the whole Netflix database all around the world. You can do that on a plane if you want a little bit faster response time, but still we're talking about how. If you want to play online games and I don't know, play Call of Duty, and you want to click and you want your lag to be as minimal as possible because you want the other player not to move around as you shoot, then you're not optimizing for throughput. It doesn't. You don't need to send a lot of data. You just need to send a few coordinates where you're trying to shoot, but you want to send them on the server very, very fast. You might use a network link, a fiber optic link under the ocean to have a very, very low response time, not weeks, milliseconds, but you are transferring much less data with respect to a ship full of hard disks. So these are two systems that are optimized for two different purposes. In this case, they are physical systems, so they have to be built. You cannot change them quickly. But on IT, there are some parameters that can be changed very quickly and change dramatically the amount of some of these performances. You can change the amount of code that an application is using by spawning up more processes. This can be done quite easily. Usually, it's just a parameter in some file. And it might use more resources, but provide a lot of more throughput or decrease response time. The effects might be fine. Okay, when we are doing performance testing, we are trying to evaluate how a system, an application, a website, a batch application, a database, whatever IT application is performing with respect of some of these properties. Throughput, response time, consumption, let's say this is another one. So first of all, nowadays in most of our customers, performance tests are done on a hurry. What you do usually is building your application, and you have a date which your application will be deployed. You are building the website for Media World for the Black Friday, all the new customization and the offers and everything. You have to deliver it before Black Friday. If you do it later, it's too late. Your deadline is done. So you spend most of the time developing the software, and then when the software is done, you do the performance assessment. So functionally is fine. Then you have to check that it is able to support the workload and all these kind of problems. So it's done in a hurry because you have a deadline, and you need the software to be completed to test it. Otherwise, it's impossible to test it. The first thing to do is to understand how people are using the software. So if you are building an upgrade of your software, for example, you might have already some production logs of people who were working with software. You might have a trace of database queries that are run on your database. You might have the logs of people interacting with your application on the phone, which is producing some requests on your website or these kind of things. The first thing to do is to understand how users use your application in a meaningful way, identify the cluster of users and reproduce them, replicate them as scripts. There are many performance software, the free ones like JMeter, for example, or Locust, or enterprise one like LoadRunner, Neoload, or there are a lot of them that allows you to replicate as a script in different languages what the user does. There are some also theoretical approach to do this. You build Markov chains of the calls of the different part of your application, and you assign weights depending on how user navigate your application. There are many different ways, simple and complex one, to simulate, to understand what your user is doing. When you have this script, you clearly deploy the script onto your application. So you need to have a production environment or something similar to your production environment, and you need to run the load. So you spawn up a few or some many virtual machines, and then you run your code, you stress your application. And then you gather the metrics. The metrics are, for example, response time and throughput, as I said before. But there are a lot of deeper metrics, like consumption, CPU consumption, network consumption, or some internal metrics of the different languages, like how much, in the Java example before, garbage collection is done, how many times it's called, how much time it takes. There are a lot of metrics that you can gather. We will see later an example of this, of a test like this. And then you look at the metrics, try to understand what's happening, try to go deep. You find a new metric that is strange, you don't know the metric, you study it, you find what's happening, if it's fine or if it's not, and then you finally give an evaluation. If the test was fine, if it matches your key performance indicator. At the very beginning of the test, you might say, okay, I want this page to load in less than 2 seconds. Or in an example that in an example optimization that we did, they were introducing the instant bank transfer. Usually when you do a bank transfer, it takes a couple of days to process the transfer. There is a European regulation that now you can do instant bank transfer, and it has to be executed within less than 1 second, for example. The company that we were working with were all the parts of the transfer and checking from a security standpoint if the transfer was fine, if there is a fraud there or something like that. They have to do this in less than 300 milliseconds, all the checking and the transfer of the different accounts. So they have these requirements, the response time, for example. You set this goal at the beginning and check them at the end. If they're fine, the test is fine. If they're not, then the test is not fine. And guess what? Usually the test is not fine the first time. This is more everywhere. There is something wrong. The consumption might be high. Some KPIs are not met. And then you change something in the application, you understand what's going on, understand why the test was not fine, and then check, try to evolve the application or change something. This is a script we will see in a minute how it's done for real. This is a software which is called Grafana. It's a software that allows you to plot different metrics. And this is an example of what you see when you're looking at this metrics. Here you see we're using the benchmark for database, actually. It's called YCSB, Yahoo Cloud Suite Benchmark. And we are, I think we were testing MongoDB, which is a database. We are trying to inject some load, so do some queries on the database. And you are seeing here the update count. So the number of time, the throughput, the metric we saw before, in a specific time frame, a specific test like this, how it was varying. So this is the amount of load that is done in the system. And another metric that we are seeing here is the CPU utilization. So the other line here is how much the CPU of this server is used. These are two performance metrics that we usually see. This is one test, and on the other part of the slide, you have the other test, and you see two different patterns. You see the maximum throughput that was increased. So if here we were doing most 50,000 queries per second, over there we were about 60. Here the load is quite spiky. There the load is much more sustained for some period of time. You have some minutes where you consistently do 60,000 queries per second, but then it drops. CPU utilization is more or less the same, is a little bit higher there, but also more throughput. So you have to do this kind of analysis to understand which one is better. from some standpoint, the other one, the left one might be better. From other standpoint, the right one might be better. So this is what you see when you do this kind of analysis. If you have any questions, try to sum them up at the end. You can proceed with the flow, and we'll try to answer all your questions at the end of this part. So now Stefano will show you this in real time. So try to use the software and understand what it means doing it live.
Okay, so yes, we will see a very simple example, a toy example, on what does it mean to do a performance test. So actually, we will test the performance of MongoDB. MongoDB is a very widely used NoSQL database, and if you remember the previous slide, we need to understand what our users are doing, and we need to develop some scripts to emulate the users. So since this is a toy example, we will simplify quite a lot this part. Use YCSB. YCSB is a tool to stress test a database, to inject some load on the database, and comes with some predefined workload patterns. So we will not simulate real users, but we will stick to the predefined patterns, and they are just making some read operation. So we have a lot of users just doing read from a very simple table on MongoDB. The other part of doing a performance test consists in actually creating entire infrastructure to run your test. And to do that, we simplify quite a lot, since this is a for example. To do that, we use this software here, which is Ansible. So this slide, we have 3 blocks, and they means that we will create 3 machines on AWS, Amazon Cloud. On one machine, we install our database, MongoDB. On the other machine, we install the load generator, YCSB. And the third machine contains Ansible, which is a tool that automates all the setup process. So basically, we have some scripts that update the operating system, install MongoDB, set up all the directories and permission and so on. Then we have Prometheus, this one. Prometheus is a time series database, and we use that to collect and to store all the performance metrics. So in Prometheus, basically, you give it a list of endpoints, HTTP endpoints, and every 15 seconds it connects, it reads all the available metrics, and it stores them. And then you can later run some queries on these. Finally, we have Grafana, which is this last logo here. And Grafana is a tool, a software to create some dashboard. So basically, we use that to view the data we have stored in Grafana, in Prometheus. So Prometheus is a database, and you can view Grafana as the interface to your database. It's not an interface, but who cares? So here we will not run the actual experiment live because they take quite a long time, some hours. But if you want to replicate all these tests, you can go to my GitHub repository. You can find all these scripts. You can create some machines on AWS, and you can run them by your own if you want. Also, if you do that, in my opinion, it's quite useful because you will learn how to use in a very basic way Ansible, Prometheus, and Grafana, which are quite useful. You can use them to monitor your Raspberry Pis. You should have them. And here I just go to the results. So we start by running some very short, very quick performance tests. They last 30 seconds each. The first test, we simulate 16 users running requests at the maximum speed they can go. So every user makes a request to the database, receives the answer, and makes another request immediately. For the second test, we have again 16 users, but then we do not let them run at the maximum speed, but we put a throttle basically on the speed. So they make a request, they receive the answer, wait a little bit, and then they make another request. For the third test, we run, we change the number of users during the test, and we let them go at maximum speed. So we run all these tests and we collect all the performance metrics, so the throughput and the response time, and I use all this data to create these very bad-looking plots. What are they? Let's start from the first one. Here we have, I don't think you can see them, but we have some dots. Each dot is the result of one performance test. On the x-axis, we have the number of users, and on the y-axis, we have the throughput of our application. And this is basically the third test. Okay, so we increase the number of users, and we see which is the maximum throughput. So if you have done some courses on queuing theory, you should be familiar with this kind of plot where you soon find the maximum throughput can be sustained by the system, and then you basically you stay there. You cannot go higher than the maximum throughput. On this second plot, we have the response time depending on the number of users. And again, this is the kind of plot that you would obtain from queuing theory. On the third plot, we have the number of users and the response time. So what I'm doing here is I just consider the very first experiments up to 16 users. Then I make a very simple linear interpolation, and I have a prediction for the remaining number of users. And you can see that more or less this is matching with the reality.
So to put it in context, try to imagine the example before. So you are hosting a website that is selling something. So you might want to do something like this in order to identify how much your server can support. So in this example, I can provide at most about 5,000 requests per second, and this can be reached with 10, 20, 15, something like this users in my system. So at most, I can have 15 users concurrently looking at my website. If I have more users, then the request is the same. That means something is happening. What's happening is that the time that they are waiting is going up. So if I have a goal, like I said before, if my page doesn't load in 3 seconds, in 15 seconds, I get bored and I go to a competitor, then I would say, okay, I want to set a limit on the time it takes to load the page. And this limit is how long you wait before getting bored. Nowadays, you wait for 3 seconds for a page to load, you're already bored. So you say, I want to be at most 3 seconds. So with at most 3 seconds, how many users I can support on my system, knowing that they cannot experience the response time higher than 3 seconds, I go back here and I can support at most 10 users, 5 users. If this is true, then if I expected that during Black Friday I have 1,000 users, I can spin up some replicas of this application, and I will need, for example, 100 replicas of this application for that day, and maybe 10 replicas for the whole next week for my normal work. this is an example of what you do in theory and with the benchmarks in a more realistic context, in actual context that you use every day.
Also, if you go to the repository, you should find an Excel file with many more data on this if you're interested. But basically, let's say that we are happy because we have a limit of 20 seconds, and so we can support 100 users, and that's okay. So we look at this and we are happy. Unfortunately, this would be very bad because, as I told you, those tests are very quick. Each point is only 30 seconds. So what this is actually telling us is that we can support this throughput with that response time for that amount of use for 30 seconds, which is not really a nice guarantee. So we run a much longer test. We use 16 users, we let them run at the maximum throughput, and we go on with the test for half an hour, no, for 1 hour. And we see that after half an hour, the throughput dramatically drops. So we start from being able to have a throughput of 4,000, 5,000 operation per second. After half an hour, we have a problem. Which is this problem? We have no idea, basically. From this graph, we cannot tell what's happening to our system. So this is where we resort to Grafana and Prometheus, and we go have a look to understand what's happening to the system during this test. So if I can open. You can access this website, which is Grafana. It's open to the world, so you can access that. It will ask you for a username and a password. They are both user. So user, and you can log in. What are we looking at? These are all the performance metric collected from the operating system of the MongoDB server machine during the hour where I executed the test. So we start from 10 o'clock and we end at 11 o'clock of this morning. And as you can see, something happens after half an hour. You will see what is happening, but you can see that basically the time frame is matching the one of the previous plot. So we have quite a lot of stuff here. The first one is called basic, then we have memory basic, network traffic basic, disk space use basic, and then you can scroll down. If I'm able to scroll, and you can see that you have quite a lot of stuff. So basically, this tells you everything about your machine. Let's start from looking at what the CPU is doing. This is kind of similar to what you see if you press Ctrl-Alt-Delete on Windows. You have the plot of the CPU. But we have something more. We have the various mode of the CPU. So we can see what the CPU is doing. We have busy system, busy user, busy IO wait, busy error, busy other, and idle. Idle, which is the green one, means the CPU is doing nothing. So before the test and after the test, the CPU is doing nothing, and that's okay. Busy user is the CPU is doing some computation in the user space mode. So it is executing some actual program. And this is the blue part, which is quite a lot here. So when we are we are executing our test workload and the throughput is nicely high, we have quite a lot of busy user. And we like that because it means that we are using the CPU for some useful stuff. Then we have busy system. This means that the CPU is running, but it's running in the kernel space. So basically, we are in some system calls, and that's okay because this is a database. We will have to do something with the storage, basically. And finally, we have the busy I/O wait. Busy I/O wait means that the CPU has something to do, so it's not idle because it should be doing something, but it cannot do this thing because it is waiting for some input-output operation to complete. So we are basically waiting for the disk. And we don't like it because it means that our disk is very slow and we are waiting for it to read or to write, and we cannot do anything in that amount of time. What we see actually is that after half an hour, the I/O wait time increases up to 100%. So basically, this means that our disk has become slower after half an hour. Why? We can go down. You can see the network traffic drops because the disk is low, so we are not answering back to YSSB. Nothing happening on the memory. Here we have some more detail on the CPU, but basically it's the same story. Here we have some interesting plot on the disk part. So let's start from this one. We have the input-output usage read-write, and this is basically the kilobyte per second, megabyte per second that we read or write to from the disk. And again, after half an hour, this drops dramatically. The same thing happens on this graph here, which is disk IOPS, which stands for output operation per second. And this is the number of input-output operation that we do every second. Again, it drops, and it drops on the only disk that we have on this machine, which is XVDA. Why is this happening? So you can have a look at the web page. As I told you can reach that from my repository. But I don't think you will be able to spot any problem. The only problem is that the disk is not supporting our amount of operation. So to troubleshoot this, you need a piece of information which you probably don't have, and that is that when you create an instance on the Amazon cloud, you have this concept of burstable IOPS. And the idea that you create your instance and you start with a certain budget of input-output operation that you can perform on the disk. Every minute you receive some credit in terms of input-output operation. So let's say that you start from 100 and every minute you receive 10 operation. If you run a workload that is input-output intensive, you will use your input-output operation faster than you receive them from Amazon, basically. So at the beginning, you have the starting credit, so you can do as many as you want. But after a while, you will deplete all your credit, and then you will be forced to use only the one you receive from Amazon. So this is our problem, but to troubleshoot, we need to run a performance test, which is quite complex, and we need some technological information, which is not available to everyone, let's say. So if I can go back to okay, so this explains what's happening on my machine. Okay, nice. So let's solve the problem. And to do that, you can go on Amazon and buy some disks. I mean, you can go to the Amazon Web Service page and buy some virtual disk. Not saying you should buy a disk physically on Amazon. And you attach this disk to your instance, and if you buy a proper kind of storage, you will not be limited in the number of I/O operations that you can do. So while we rent it, we buy not one disk, but we buy 4 disks. and then we put them in RAID 0. If you know what is RAID 0, basically you, instead of writing to a single disk, you split your data and then you write parallelly to many disks, and then you can read back them in a parallel way. So ideally, if you have 2 disks, you are twice as fast. Okay, so we do that. We run another test, and we get the red line. So we have solved the problem with the throughput, and so that's okay, because these kind of disks are not burstable, so we can do as many operations as we want, more or less. However, the maximum throughput has dropped quite a lot. So we are using 4 very expensive disks, but the performance are really good. So we are paying quite a lot of money, but we are not happy with these results. So we have a new problem, and now the performance are not good for us. So again, we could go to Grafana and check a lot of stuff, and this time we wouldn't see anything strange. So there are actually no problem with this setup. What we do is, as any engineer, when reading the manual fails, to try something at random, and maybe it works. So from 4 disks that we were using, we keep on 1, we remove the RAID, and theoretically we should be 4 times slower. Instead, it's actually the same. So the red line, which was before, with 4 disks, and after the yellow line with only 1 disk, it's the same throughput. So we can reduce our budget by 75% and get the same amount of performance. And this is quite strange. However, still the throughput is not okay for us. So what we can do this time, so we have tried to change the hardware where we run the test. The other thing that we can do is to change software, or to reconfigure the software. So you know that when you create, when you attach a disk, in order to use it, you need to create a file system on the disk. And you know that there are various types of file system, NTFS, FAT32. So here we are using XFS, which is the suggested file system for any database. And actually, if you go to the documentation of MongoDB, it says that you are strongly suggested to use XFS. Let's see if they are right and move to ext4, which is the, let's say, default file system, or most commonly used file system in Linux. We get the green line. So we have a much higher throughput by spending actually the exactly same amount of money, because it's only a software reconfiguration. And this time, this matches my requirements on the throughput, so we are happy, and we can go on. So what's the point of this very simple example? First of all, the theory is correct. Queuing theory can give you some reliable predictions. You can, of course, use that. However, there comes a point where the theory cannot help you. There are things which cannot be modeled, or at least they are very difficult to model. So you must do the real performance test. And moreover, when you have a problem, in order to solve it, you must have some technological knowledge, like knowing how disks work on AWS. Imagine if the problem was on the JVM or the configuration of MongoDB or whatever. So you need to have all this knowledge. Furthermore, we have seen that by changing a very simple configuration, we can increase quite a lot our performance. And however, it's very hard because here we have changed only one parameter, but why did I change the file system and not the amount of RAM? I don't know. So there are a lot of things that you can touch, and you need to know what you are touching. And the last thing that I want to say is that here I'm not saying that MongoDB is wrong. You should use ext4 and XFS. The point is that the optimal configuration depends on the type of workload that you are using. So for this toy example, XFS was not good. Probably is good in real scenarios or in real cases. So I'm not saying I'm not on MongoDB. Okay.
Okay. So the first thing I would like to point to you is the fact that we did a deep dive in one specific case. In order to solve this case, we have to rely on a lot of expertise. We applied a methodology which is called the U method, which stands for utilization, saturation, and error. So this is a method for performance analysis that we use a lot. Stefano showed you some utilization metrics, utilization, and we identified the saturation on the input-output operation that we could do. There were no errors, unlikely, in this system, but this is a methodology that is quite general. We can use to understand most of the performance issues in many systems. We have to know how to apply this methodology. We have to know how Mongo is working. We have to know how AWS is working. We have to know about the different modes of CPU of your that CPU is working in a Linux environment. We have to know a lot of this stuff. And this changes completely if you change the application or the environment, the operating system. Or so here you saw a change in the software configuration, the file system, that had a dramatic effect. If you think about the modern application, they are usually run on hardware, which might be virtualized on the storage layer, network layer, on the CPU layer, which might be local in a cloud remote. And these have a lot of configurations. What kind of disk you use? So one configuration there, but you have a lot. You can run a virtual machine with a lot of cores and not much memory, a lot of memory, not much cores. That depends on what you're doing. If you want to run an in-memory database, you might not need a lot of disk, but you need a lot of memory and fast access to the memory. You have a strange hardware configuration like NUMA nodes. If you have a system with many CPUs, they're not connected to the whole memory. Some bunch of the memory are connected to some CPU, some are other. This is called non-uniform access architecture. This is one of the things that you have there. So depending on the kind of choice you made on the hardware, has some impact on the performance, and a lot of choices that you can make there. You have the operating system, which have many parameters. You have parameters that tells you how to schedule the process on the CPU, how long they can be scheduled, when they can be interrupted. You have parameters that tries to optimize the usage of disk. When you read something from disk, you might want to use the fact that you are spinning this, for example, and you're already reading some bytes, and the next byte is quite cheap, to read a bit more and store it in memory. You might do it later. So this is called read ahead, for example. This is one parameter of the operating system. There are hundreds of parameters there. Then you might use running Docker containers, which have some limits on the amount of memory and CPU that you can use, or on other metrics. Then you have the language that you use, runtime of the language that you use to run your application. Java has more than 700 parameters in the latest versions that can be changed. Then you have your parameters, connection pools, and everything else. So if you sum up all the different parameters, you're not only summing up, but some of them has an impact on other parameters. If you find the amount of possible configuration for your application to run, that you can just specify in simple configuration files, the total number of configuration is something funny like the number of atoms in the universe, the number of seconds since the Big Bang, so these huge numbers that are quite hard. So in previous example, about those billions of configurations, we tried 4, and we were lucky that one of them was good, the other 2 were not as good. So finding those for configuration requires a lot of expertise. But we see that the improvement is quite real. So this is a paper that we published in 2015 on a case that we did manually, so manual optimization in one of the biggest Italian insurance companies. So this is the utilization of their data center. This is an actual data center, so a building full of servers that is using a lot of energy. This is the utilization of their instances that were serving their customer workload. Usually, these are working days, so this is a pattern that you usually see. So people start working in the morning, have a lunch break, and then work in the afternoon, and then stop working. This is an insurance company, so on Fridays they work a bit less, they stop earlier, and this is it's called the model distribution. It's quite common in this context. So in blue, you see the CPU utilization in an average week. The workload was more or less the same, and in red you see the CPU utilization after some optimization. You see that after some optimization, for the same amount of work, so the same amount of job that people were doing, so in this case, trying to evaluate insurance policies or things like that, the CPU utilization was cut by 5 times. So this data center, you can shut it down more than half and save a lot of money in terms of licenses, in terms of energy consumption. So this was a huge success for them because they could save about millions of euros for some of these kind of optimizations. And this happened only by changing one parameter in the JVM, deployed on thousands of JVMs. So this is the impact that this kind of activity can have. Today, performance tuning is like driving an airplane. You have to train as a pilot for 10 years, for example. You have to be certified to run a specific type of plane, and you have all the controls there that allows you to change everything, every bit of the airplane. You can shut down the vacuum of the toilets with one button. You can change the flaps with another button. And clearly, you understand that if you run the wrong button, some bad things might happen. But what's Boeing, Airbus, and everyone is doing in this context is adding one more button, which is called autopilot, and then you leave the autopilot on most of the time. But you still need to have the knowledge of everything to be able to run it. What Tesla and other car manufacturers are doing is trying to do the opposite. So bring me there, and I give complete autonomy to the vehicle to drive itself, to understand everything, to change the floor configuration, change the speed, the brake, and this kind of thing. This is what we're aiming to do with Akamas. So instead of trying all the different parameters and configuration, all of them, we want to tell Akamas, hey, I want to run as fast as possible, or I want to consume as less CPU as possible, but I'm not interested in response time or these kind of things. These are requirements. This is like bring me home or bring me to the basketball court, and then this system is driving itself to the best configuration. These are some of the results that we do, that we obtained. These results are read like this. Every dot here is a performance test with a different configuration. This one is the baseline. So in this case, we are optimizing another database, which is called Cassandra. We are trying to increment the number of requests, similar as we did with Mongo, increment the throughput. We start with the baseline. So this is a default configuration that it comes with the database as this amount can support this amount of requests. And then we try different configurations. We try some bad configuration, we try some very good configuration. At some point, in just a few hours, the algorithm converges to find a quite good range of very good configuration that are able to more than double the amount of throughput for the same system. These are the software configuration. It doesn't cost €1 more to run this database. But it provides you twice the throughput. These are other examples that we did. This is Spark, which is a big data framework that is used to run programs that are analyze a huge amount of data in a distributed way to gather some results, to understand something about this data. And one of the key factors here is how much time you take to analyze those data. If it takes you 2 hours to analyze a set of data, you might you write your program, you start it, and then 2 hours you have an answer. It's quite different if it takes 5 minutes. If you write your program, 5 minutes later you have your answer, you might change your program, do a lot more analysis. So as a data scientist, the amount of time it takes to analyze the data is a huge factor in how many analyses you can run and how much value you can get from those data. In this context, we were trying to reduce the time it takes to analyze an amount of data. In this case, we were running PageRank, which is the algorithm invented by Google to index all the pages on the web and allow you to search these graphs, let's say. So it's an open source implementation of PageRank in Spark, and with a set of data, I think it was the Wikipedia set of pages, we were able to reduce the amount of time it takes to build this model, to analyze this data set from 22 minutes down to 5 minutes. So instead of launching your computation and going for lunch, you can launch your computation, have a coffee break, and then come back, change something, and do it again. These are some examples in different contexts, but it can be applied in many contexts. So how we do it? So first of all, we use the schema we thought. So we do a performance test. So we evaluate in the real system. We are not building models of the system here. And then instead of just evaluating the test, we use something, this brain here, which is our machine learning algorithm, to find a set of configuration that is applied on the system, and we do it all over again. So this is continuous performance optimization in the sense that it continuously optimize the system with different configurations. There are many different models, many different techniques that you can do this, use in this context. Going back to the analogy of driving on building an airplane, usually you can, first of all, build it on paper. So writing down the equation for the fluid dynamics of the air, that if your airplane should fly. And in this context, you can use queuing network, Petri networks. You can build some models on the equations that we know are valid in the context of performance. Then the next step is building a simulation. So you build your airplane, you put it in an air tunnel, and you see how it reacts. This is still not a real airplane, but it gives you more information on how it reacts to a real environment and allows you to change it a bit. It's much more expensive than just writing a project and on your laptop and solving some equations. It requires some data, it requires some tests, so it's a bit more expensive, but it's much more realistic. The final one is building the airplane and try to fly. If you fail, you crash your airplane, it's quite expensive. Someone might even die. If it works, it works. It flies, you're done. In our context, it means running the performance test in a real production environment. It's very expensive, but if it works, it gives you a lot of confidence on what you're building. In this context, you cannot do as many changes as you want, since they are very expensive. So to identify the best configuration, you have to rely on some kind of optimization techniques like reinforcement learning, and in particular, we use Bayesian optimization, which is one of these techniques. How Bayesian optimization works? In a very, very simple context, we have one parameter. So not the 1,000 that we saw before, but just one, otherwise it's impossible to plot them. We see two parameters there, but one is fine. We have the performance of the system that we don't know. The red line here is the performance of our system in terms of a metric. And you see there is also a gap, a red gap here, because it's uncertain. There is some noise in the system, so we don't know the client. We are interested in minimizing it. So we want to find a configuration about here that more or less in half of the x-axis that minimizes this configuration, like a response time, for example. We don't know anything, so our current knowledge of the system is this green line, and we have a lot of uncertainty there, so we know nothing. We sample some points, so we do some tests. We do two tests, the beginning at the extreme of the interval, for example, and we gather some knowledge of the environment. Then we build a function, which is called an acquisition function in some way, that tells us which point to try next. We maximize this function, and we find out that we want to try this point here. So we sample another point. We are not interested in learning perfectly well this tools here. We are not interested in configuration with high response time, because they're bad for us. And we want to minimize the number of tests that we do, but we still want to get there. So this is the main goal of this optimization activity. We see that point, which is likely quite good, quite near the actual optimum, and we update the knowledge of our model. This is usually how reinforcement learning runs. We give some knowledge on the system, it reinforces this, update our model, and then use the updated model to sample another point. You see that the acquisition function changes and allows me to sample another point. By going on in this way, we test some configurations, and at some point we find out that we test a lot of configurations near the optimum, and not a lot of configuration in other places. We have a quite good knowledge of the environments. This is still uncertain, but it's fine because we have found our solution. And this minimizes the number of tests that we need to do. This, at the high level, is how Byworking should work for this kind of environments. Here we see an example with 2 parameters. This surface here is the same as the other one, but in a 3-dimensional space. We have some minimum that are here and here. There is another one later on. So there is a very smooth surface. We know nothing about it. You will see the video will start with a flat surface. We know nothing about the environment. And then sampling points to learn the way this surface is doing. So this is the answer. So you see that the shape of the model is changing as we sample points. A lot of points is a very interesting area. We sample 1 point here, 1 point there, the non-interesting space, and we know nothing more or less about them. There is a lot of uncertainty here. At one point, we go out of this area and we find the other one. So you see that we are also sampling points here. Then, when we are fine with the uncertainty here, we sample some points in other places, and we find there is another minimum there. At the very end, we sampled a lot of points in these 3 areas, in the 2, 3, 4 points in the other areas. So we spend a lot of time interesting the regions and less time in area that we are not interested in. 1 dimension, 2 dimension, we usually do problems with 10, 15, 20 dimensions. They cannot be depicted, but the complexity you get is getting higher and higher. So this is what Akamas is doing. We evaluate our research approaches with state-of-the-art testing in terms of 2 metrics, the best so far. So given an optimization, how good are we at finding the best solution? How quickly we can get to that solution? And the other, so the best configuration we found. The other one is so finding the best configuration, we get the integral of this, so the area under this curve. And the smaller the area is, it means the faster we are getting there, and then we are not going somewhere else. We are getting there much faster if we can reduce this area. The other one is the regret, which means is how bad I regret it if I try the configuration that is wrong. So not only finding a good solution, a random search finds a good solution if given enough time, but we have to stay in that good area. So we have not to waste time in some places we don't like. So this is the regret, another method that we see. We compare ourselves with respect to some optimizers, some random optimizer, and one of the optimizers done by Twitter, which are state-of-the-art in this approach. And we find our optimizer both in regret and under the curve are better in finding faster solution and better solution. And that's why Chuck Norris approaches. So if you're interested in what we do, you can obviously ask some questions. You can write to my email. We are developing these approaches by ourselves. So Stefan is doing his PhD on these topics. We are building a product that does use this approach in real environments. And we evolved this approach doing thesis on some parts of the algorithm or some technology. And in our office in New York, we are certified. No, So that's, if you have any question, please ask them now or
okay, so let's first thanks Giovanni and Stefano for the presentation. Well, now is the fun part, because all of you, if you are interested in any of the things that I've shown to you, there are many different things with several different applications and stuff. All the things you can now ask them if you're interested about something, if you want to learn more about something, and we can start having some Q&A. So don't be shy, please, like you always do in the course, and do more questions, since this is not, you know, things we are evaluating. So you could just freely ask to them if you are interested about something, okay? Any question then? Come on, guys. So really no questions. So maybe from home, let me check if we have some questions from home. Okay, so if you have no questions,
I invite you to...
Oh yes, there is one question over there.
Sorry. The question, so everyone is curious. The question is, you try to an internship would be a problem if your headquarters in Milan and there will be projects there or another customers. If I am here in Padova, how can I do it? So, so usually for a thesis, we do some remote thesis. We have done a thesis here with Luca remotely. In other occasions, people we like to do their thesis. In other ways, you can work with us. We have recently opened last month an hub, so an office here in Padova. There are some other colleagues, some in the performance area, but also some in the security area, which do their day-to-day work here in Padova. So you can definitely use that space over there. The kind of project usually depends on what kind of things you want to do. I usually do also some interviews for people that want to join Movieri. Part of doing interviews for candidates for an internship or a full job. And I invite you to check the Stefano repository, because some of the software that you see there is something that I usually ask for if people have seen it during interviews. So finance, automation, or similar things. Is something that for an internship you will usually learn them during the internship, but if you want to work in these kind of fields, something is usually accessible in these automation software that are very, very well evaluated by evaluators when you apply for an IT job. So you can definitely do some of this in Padova. Depending on the team you're working with, you might be asked sometime to land for a couple of days, for example, but we have a hub here, so it's easier for you. You're lucky this is the first one in Italy. That's on the opinion.
Okay, so other questions? Otherwise, I have one question. So, like, you know, all the students here, most of them at least, have basically spent most of their studying, so like doing university, and they have never been, you know, out of work. So the thing is, everyone tells that, you know, once you finish, you're an engineer and you can do a lot of practical things, but in reality, like in real terms, what does it mean for you people that have a lot of real experience? What does it mean to be an engineer, and what you do when the university finishes? So if you have like some advice or some things that they can get out as take-homes.
Okay, so I spent a lot of time in university. I did my master in technical information technology, then I did a double degree in Chicago, and then I spent my PhD in Milan with a period in the US. I spent a lot of time with the research field in the university, and I was very expert in one particular field. During the PhD, you become very expert in your particular area. And then when to out of the university field to looking at some customers, the first thing you want to do is to keep learning a lot. So you might be very expert with respect to people that are working since several years in the field. You might be very expert in some new subject. Machine learning was not taught in the university since the last 5 years, probably, maybe even less. So if you are out of university now, you have some knowledge that some people do not have. But they also have a lot of knowledge on how these complex enterprise worlds work that you cannot get here. You have hands-on experience in using this software or similar software. It doesn't matter if you're using a file or another one. But this kind of the methodology behind that is quite well established, and it's not something that you can really learn without putting your hands on. So the first thing I started not in the development. I'm now head of engineering, so I'm managing the development team. But I started as a consultant performance area. I go into customers and looking at the performance data, finding the issues. I was once in a bank in Parma trying to understand why the system was running slow, and I had to deep dive into metrics related to virtualization of machines, the contention of different virtual machines on a physical CPU, asking them to move to a different hypervisor to optimize this kind of workload, and suddenly getting better at the problem. I learned most of these during that period, studying that specific technology, and that's something that you cannot do if you don't get your hands dirty on these stuff. So I encourage you to get your hands dirty. You can even do it on your laptop. Stefano is monitoring his home temperature, the humidity of tomato plants, making coffee from his laptop, getting the temperature of the coffee maker, these kind of things with Grafana and kind of tools which are the same things in an enterprise world. They're open source. So that's another big point. A few years ago, there were closed source enterprise software you have to buy it in some way for your laptop. And then but nowadays you can do a lot of these things by hand or with small investment with an Arduino or these kind of things. So try to do this, try to get your hands dirty, and then you will find that most of the things that you see later is another way of applying what you already did with your hands. So I first started looking for a job that allowed me to learn more, even more than I was already learning.
Okay, thank you, Giovanni. So another thing that maybe might be quite useful for them is that we were talking before, and you were telling me that you have done some interviews for hiring people. So there's always a problem if you finish the university to understand how you should do your CV, what is really relevant to put there, what is highly relevant, and how you should present yourself if you want to work in some specific kind of company. So maybe there are some kind of advices also there that you can provide them to understand what Movieri is looking for. Overall, what should an engineer look and put in their CV to be more, interesting in the work, in the world of outside university. So if you have any suggestions, or Stefano, both of you, please go.
If you are going out of the university, usually you are applying for a junior position. The main goal of a junior is to learn about context, about the environment, about the technology, the methodology there. So to learn, you have to be humble. So if you don't know everything, so you have to be that you don't put in your CV, that you show during the interview. And you have to be curious. You have to ask questions to the interviewer. Part of the interview is the interviewer getting to know you. The other part is you getting to know the job. Because you have to get out of the interview knowing I want to work for this company or not. And then the interviewer get out of the interview. I want this guy to work with me. Next seat in the next seat since now. So it's a two-way process, the interview. I have convinced you to come to work for my company during the interview, and you have convinced me that you are a good fit for my company. So for the junior position, curiosity and humbleness are two good points. From the technical point of view, if you have any hands-on experience, you'll be down. Even automated my confirmation maker is fine as we highly like to read about it. If you have, if I do an interview, if I have time, I try to check if the guy has some GitHub repo and look at the code that they write on GitHub. If it's a development interview, for example, if you have a public GitHub repo that you clone something and you change it to a request that's something from a developer point of view that I value, so I can see your code. Then the interview process might have some challenges, like ask you to write some code, do some testing, these kind of things. But definitely that's something if you have an open source contribution from just clearly the example that you like the most. Maybe they're not the one that you were the most or high, but the one that you like the most, that you study the most, that you want to invest on is something that I usually when I find someone that is a bit shy, I ask you what's the exam that you like the most in your class. So tell me about your thesis. You should be passionate about your thesis. You should be able to tell me your thesis in the details. You should know more than me about your thesis. So this is some things that I usually look into.
Okay. So if there are no other, okay, there are questions. Yeah, sure.
So the question was if you have to write down some proposal for the thesis or the internship. We have some proposals. So we are a product company. We are a product that is self-custom. So when we do some research, that is focused on the problems that customers ask us. So we find some theses that are in different contexts. They might be technological theses, research theses. So we have some proposals for you for problems that we know are open and are core to our future businesses. This is for us is not looking. And we usually have some proposals, and we can show them during an interview and you see it.
Okay, so if there are no other questions, let's thank again our speakers. And so basically, now you have the email if you're interested in doing thesis together. We already have done previous years other collaboration with them, after collaboration with them for master thesis. So if you're interested, you can do that. Just that you know, the reason why Nicola is not here together with us and it's from remote is because he had to be in quarantine for COVID reasons. So that's the reason why he couldn't attend here today. So not because for other reasons, but just because that. And so if everything goes smooth from next week on, we'll be back again. And regarding us, we will see tomorrow again for our lecture. So you can, lesson integration. Thank you.
Okay. You want to know more about this? We have some flyers.
Oh, okay, so if you're interested, there are also flyers here before leaving if you're interested.
Do some